He says they're never going to widen it too. He says it'll never happen. So people just won't give up any
space.
Yeah. And then they think people will travel there and it'll be louder. Which is actually probably true. Okay, I think it's time, at least according to this computer clock. So the homework session is tomorrow, right? And I don't think I mentioned this before, but you want to at least look at the problems for the discussion to be efficient. You want to be aware of the problems. Now I know a lot of students come in cold, but it's to your advantage if you at least look at the problems. If you can try to do some of them, that would be even better. Okay. And again, the homework is really just for you. I'm just checking it off, but it's you can learn a lot from the homework, right? And the quizzes are based on the homework to some, not completely, okay? Sometimes I'll get into something we did in lecture, but not in the homework. That can happen on the quiz. Okay, so, another thing. So I'm going to be I'll send out an email message. I'm going to be posting the quiz on Sakai for everybody. So you guys, you guys have to go to Sakai, okay? It's in resources. This is what I use. Gene has told me it's not very good because to carry over to the next class. But anyway, this is the simplest thing for me to do. And then Gene is sometimes posting other lecture notes elsewhere that's easier for you to get at. I don't know what he's going to do with the quizzes. So, but if you go into resources, you'll see everything's going to be there. And there'll be a quiz folder that I'll institute probably tomorrow. Yeah, tomorrow. And quiz 1 will be in there. Okay? Is that clear? All right. Okay, so we got into Euler's equation. This is Newton's second law for a fluid in the absence of the presence of only pressure forces, no gravity, no viscosity. And so it's F equals ma. We found F. A force on a fluid particle occurs if there's an imbalance in pressure on it, and it's actually simply the gradient. The force per unit volume is minus the gradient of the pressure. That's going to be the mass, which is easy. It's just the density times the volume, our little volume here. And now the acceleration. And it's surprising that the acceleration is not the partial time derivative of the velocity here. And let me explain that to you. I don't know if this is in the book. Well, anyway, doesn't matter. So let's look at here's a fluid particle. Here it is at one time. It's at some point in space. A little time later, dt, it's going to have moved. Let's say it moves in this direction. So if it has this velocity at this moment, it will move in this direction. And over a small amount of time, it will have displaced in this direction. Now, if the time's not small, this can be a curved path. But this is all small, as denoted by the dt here. And in the limit, of course, we let dt go to, or delta t go to 0. So here it is at the beginning of the time interval. A short time later, here it is over here. And you'll notice something, that its velocity, the velocity here will approximately be the value here, but it can change by a small amount. And when you find the acceleration, here's the definition of the acceleration of a particle. You've got to follow the particle. By that I mean you've got to find the velocity at the final point of the interval minus the velocity at the initial point divided by the time interval. You can't argue with that. That's the definition. So you can see the problem here. The velocity has changed not just due to time, but due to the point in space. And that's actually due to our Eulerian description. You don't need to worry about that, but this is what we have to deal with. So we have to, we do a Taylor expansion of this, a first order Taylor expansion, and then the 0th order term is going to cancel here, and what's left over, that's going to be our acceleration when we divide by dt. But the key problem here that people, when they do fluid mechanics, tend not to see until they're told it. I think that's the way it is with just about everyone. I remember I went through this, you know. So when you look at the velocity at this point, you've got to recognize that it changes due to the change in spatial point and in time. So the first order Taylor expansion, it'll have the time derivative here. That's obviously going to be there, okay, to see how it's going to change a little bit due to the fact that it's evaluated at d plus dt. But it's also going to be a little bit different because the point has changed. So how do we get that? Well, we get it with the directional derivative. We need to, if we want to know how the velocity changes due to this change in spatial point here, we need to take the change in this velocity along this direction. That's called the directional derivative. And what it is you take the gradient dotted with a unit vector along that direction, and then you have to multiply by this little distance. You take, here, you notice how we multiply, we take the time derivative and multiply by dt to get the change in u. Here we take the spatial derivative along the direction and then multiply by dr. So I take this unit vector here and multiply by the length, and so it ends up being just dr vector. So we have to include that to get the acceleration. So what we find is that the acceleration is not just the time derivative, the partial time derivative. And that's sort of a clue that you might be wrong if you think of the acceleration as being this is a partial derivative. The math is trying to tell you something there. Maybe, I don't know. But anyway, the full time derivative, it's sometimes called the convective derivative, notated by capital D. It involves this time increment and the spatial increment. How many people have seen this before? How many people recall this in here? Well, I know you do, because you just took the course. Okay, so now we can form Newton's second law here, which is the force is the mass times acceleration. We found this yesterday, minus the gradient of the pressure times the little volume. The mass is just the density times the little volume, and now we found the acceleration. So we put this together, and here's the force. Here's the mass, and here's the acceleration. And this is written in, equivalent but slightly different ways. We're going to write it this way, okay? You'll notice here that dv, a little bit of volume scales out of the problem here, and we end up with this differential equation, and that's called Euler's equation. And now, all we care about is, for linear acoustics, all we care about is the linearized version, right? So, what's this term right here? Remember, u is a small quantity. We don't know what it needs to be small compared to. We don't know what to compare it to, but we'll get there. I guess we're not going to get to that until tomorrow in the problem set, as I mentioned yesterday. But anyway, you want to think of u as small here. This is the particle velocity in a sound wave. A sound wave is just a perturbation. In linear acoustics, it's just a slight perturbation. So we have a product of two small quantities here. This is going to be very small. We chuck it. We get rid of it for linear acoustics. So the linearized Euler's equation is this. This is what we use for linear acoustics. And as I mentioned yesterday, this is important in fluid mechanics because this is a nonlinearity. You see, it's a product of the variables here. It can cause turbulence. It can lead to turbulence. This term right here. So in the end, you can see that we didn't really need the full convective derivative, right? We didn't really need this. But I think it's just a good thing. This is fundamental fluid mechanics, so I think it's a good idea to present it here. But in the end, for us, we get rid of this. Now, if you get involved in nonlinear acoustics, it'll be there. Yep, it'll be there. So if you get involved in that in your research, or if you take the nonlinear oscillations and waves course, right, that I mentioned, 4459, you need to deal with this. Okay, so any questions so far? All right, so that's the fluid mechanics. All right, that was our diversion into fluid mechanics. We've come up with, here's a summary of what we've come up with. I'm going to list here the linearized, these are the linearized equations of fluid dynamics. There's an equation of state. This is the thermodynamics here. This links the pressure and the, in our case, the pressure and the condensation here. They're proportional, and the constant proportionality is the bulk modulus. This is the stiffness of the fluid. How the density changes with pressure. That's what the bulk modulus is, and you have to do it adiabatically because that's what sound almost always is. So this is the adiabatic bulk modulus of the fluid. Here's the equation of continuity, which expresses mass conservation in terms of the condensation. Remember, the condensation is the fractional change in density. Here's the particle velocity of the wave, the fact that when you have a wave, you're going to have motion of the fluid. And here's Newton's second law. So how many equations do we have here? Well, how many unknowns do we have, or variables, dependent variables? Well, we actually have 5, right? We have pressure and condensation, or density, change in density. These are scalars. The velocity here is a vector, so you want to think of that as 3. It's 3 scalars, right? X, Y, and Z, for example. So we have 5 unknowns, and how many equations do we have? 1, 2, this is actually 3 equations, right? 1 for each direction. So we have 5 equations and 5 unknowns. So everything should be okay here. We should be able to get solutions. And in fact, because these are linear equations, there should not be much of a problem here, okay, from a fundamental perspective. If you get into geometrically complicated situations, it can be hard to solve for this, and you have to shove it on a computer. Okay? That's what often happens in the ocean. That's why I stay away from the ocean. Okay? Physical acousticians usually stay away from underwater acoustics, okay, because it gets really complicated. And some of you may know that, and a lot of the distance learning students may be aware of that. Okay, so what do you do when you have 5 equations and have a number of equations, and you have the same number of unknowns, and they're linear? We want to solve them, right? I don't know, solve is not really the right word here. What we want to do is, the natural next step here is to beat these into one equation and one unknown. Seems reasonable, right? So, what we choose here, what people usually choose, is the pressure. We'll discuss the other acoustic variables, the condensation and the velocity later, but we're going to head towards the pressure here, finding one equation where only the pressure, all the other dependent variables are gone. Now we're going to assume, as we've been assuming, that in equilibrium, when there's no sound wave, the density is constant, okay? That it's a constant, and that the bulk modulus is a constant too. And as I've mentioned to you before, in the ocean, that's not the way that it is. Sometimes it's a good approximation, sometimes it's not. You have to deal with the fact that it's non-uniform. For example, as you go deeper, what happens to the equilibrium pressure? It goes up, right? Everybody knows that. Yeah, okay. So, but we're going to stick with a uniform system. And if you want to see the generalization of this, you can look in KFCS. It turns out what we're about to derive here will hold even if rho naught and B are not constant, as long as they're varying sufficiently slowly. And KFCS aren't really good about specifying what sufficiently slowly means, okay? But you can look in there. As long as these are varying sufficiently slowly, you'll still get what we're about to derive, okay? So how do we eliminate all these other variables? Okay? So you'll get a chance to do this on the quiz in a somewhat different situation. Okay? So this is an important, it's any kind of wave physics, it's always important to be able to derive the wave equation, the equation that's going to dictate how waves propagate from the fundamental equations. So that's why I'm putting a problem like this on the quiz. So you'll see we've got, we don't know P, we don't know S, but look, here's P and S are proportional to each other. So there's a very simple relationship there. So they're essentially the same thing. They just differ by this factor of B. I look down here and I see a U here, and a P here, and S here. To me, I don't care about the fact that this is a P and S. They're essentially the same because of this. So I'm going to focus my attention on these two equations, and I'm going to get rid of U, the particle velocity. So how do we get rid of U? Well, you see how to do it? We need to take the time derivative of the partial time derivative of this equation, and we need to take the divergence of this equation. Then we'll be able to eliminate them. Now, you may not see that right yet, but as we go through it, you'll see it. So let me show you how this works, specifically how we do this. So I'm going to take the time derivative of the second equation. Here it is. All right, if you look back, you'll see this is the time derivative. Now, these two operations here, the divergence and the time derivative, partial time derivative, they're independent of each other. So they commute. It doesn't matter the order in which I do these operations. They commute. So I'm going to interchange, bring the time derivative in here. And now here's the divergence of equation 3, right? And now what I'm going to do is divide by rho naught to get this. And now if you look at these two equations, what do we do to eliminate U? We take the difference. We subtract from the left side here, we subtract the left side here, and similarly over here, from this we subtract this. And that will eliminate U. So when I take the difference here, this goes, and you can see, we get this minus this is equal to this minus that. So the minus sign goes, we get this. We easily eliminate the condensation with that first equation on the previous page. And we get this equation, and here's how we write it. Here's how I think KFCS write it. And you should recognize this, right? This is called the wave. I'm going to italicize this. This is called the wave equation. Now, there are a lot of wave equations out there. And you actually should know this from 3119. Did you do flexural waves on a thin rod? Yeah, it's not the wave equation. And one of the reasons we do that is just to emphasize to you that you don't always get the wave equation. Deep water waves on the ocean don't satisfy the wave equation. And that has huge consequences. Let's see, well, just real quickly, one of them is when you have one property of the wave equation, as you know. Okay, so let me remind you. Small amplitude waves on a string, transverse waves on a string under tension, will satisfy this equation, but it's in the one-dimensional case. So this Laplacian here is just the partial derivative with respect to x. So you saw that last quarter. Okay, that's the wave equation in one dimension. You probably also did membranes. Okay, that's like a two-dimensional string, and it satisfies the wave equation where you have an x and a y. So now we're seeing the full 3 dimensions here in general. So one property, don't worry, I haven't forgotten about the ocean waves. One property, very important simple property of the wave equation is that all waves travel with the same speed. And that speed is this c right here, which we've identified as the square root of the bulk modulus divided by the density. So not only have we derived the wave equation, we've identified what the speed of waves is. And you'll notice this has nothing to do with the frequency or the wavelength of the waves, right? So what happens on the ocean, on the deep ocean? Anybody know? It's been known for thousands of years. Maybe even more. Maybe on the order of 10,000. I don't know if anybody knows. Okay, if you're on the ocean and you start to see big swell, the wind's blowing this way, and you have large wavelength waves coming towards you, what do? People found this out thousands of years ago. You get away from there. A storm is headed your way. The long wavelengths travel faster than the short wavelengths. Okay, so that we don't have the wave equation there. That's an example of we don't have the standard wave equation. Okay. Now, here's kind of a simple point, but I want to emphasize it. We've been thinking in terms of we have a couple parameters of our system, of our medium. It's got some density, equilibrium density, rho naught, and some bulk modulus. We're not going to switch. It's much more physical, much easier. Instead of using the bulk modulus to think of it as characterizing our medium, we're going to use the speed of sound. So the parameters that specify our medium now, in almost all cases, from now on, in almost all cases, we're going to deal with rho and c. Those are going to be the parameters of our medium. Once you know rho naught and c, once you know that you've acoustically, from a linear acoustics point of view, you've uniquely specified the medium. So another way of looking at it is if you have two different mediums, okay, they're just physically distinct. They look different or whatever, but they have the same speed of sound and the same density. The acoustics is going to be identical. Okay, so a natural question here is, remember this little p here is the acoustic pressure. It's how the pressure deviates from the equilibrium pressure, which is due to the sound waves. That's why we call it the acoustic pressure. What about the other acoustic variables? Do they satisfy the wave equation? That's an interesting question. We'll do a homework problem on it tomorrow. And it's also useful because it naturally leads to relationships among our acoustic variables. And we use these all the time, very common. So the first thing I want to do here is, because S is proportional to P and P satisfies the wave equation, S has to satisfy the wave equation. It's obvious, because they just differ by a constant, bulk modulus. But the bulk modulus is not good for us anymore, right? We want to use the speed of sound. So we will use this relationship to convert our, remember this, instead of this now, we want the relationship to involve rho naught and c, and that's easy to get, and here it is. So here's the relationship between the acoustic pressure and the condensation of the acoustic wave, differs by rho c squared. And something really important happens here that escapes some people, and even people who should know better, okay? And everyone falls into this trap. I fell into it. We're doing linear acoustics, right? So that means our acoustic pressure, the typical value of our acoustic pressure, has to be much smaller than something. What is that something? Well, what everyone says in the beginning when they're studying acoustics is they assume it's that, right? That's what you'd guess. It's not true, not in general. And this tells us, what we know about linear acoustics, this tells us what the correct relationship is. What we know about linear acoustics is we definitely have to have the condensation much less than 1. Remember, this is the fractional change in density. For our thermodynamic equation to hold, we can only have slight deviations of rho from rho naught. We made that approximation. It's like a Taylor approximation. You can think of it as a Taylor approximation. We have to have rho close to rho naught. So this is, that's a correct condition that we have to have. If we put that into here, we can conclude what the condition on the pressure is. And what is it? Can you see it? The correct condition is that the acoustic pressure has to be much less than rho naught c squared, not the background pressure. not this equilibrium pressure. Now for gases, it doesn't matter, because for gases, the bulk modulus, rho naught c squared is the bulk modulus, and it's proportional to the equilibrium pressure, and gamma is typically of the order of 1 here. So for gases, ideal gases, you can get away with this, but in general you can't, and it's not true it's not true in water, in the ocean. It is not true. You have to use this. And it has an important consequence because typically in liquids, this rho naught c squared is typically much greater. This is typical, okay? I haven't calculated this for the Mariana Trench, the bottom of the Mariana Trench, okay? So I don't, there's a high pressure down there, right? That's the deepest place in the ocean, places in the ocean. So I've never done it. I really should do it. Oh, one of you can do it, and then send me an email message, and then I'll send it to the rest of the class. I'm just looking for ways to make my life easier, right? Do you have any idea how much grading I'm going to be doing shortly? With 23 students, and a lot of them are at a distance. Okay, so, so typically, this is the case. So it turns out that in sound and water, you can have big pressure swings and not violate our thermodynamic, the fact that we linearize the thermodynamics. You can have big pressure swings. And what's happening here is actually pretty obvious. In a liquid, when you have a pressure swing, what kind of density swing do you get? Oh, I use this word swing a lot. It's sort of an old acoustician's term. It just means deviation, you know. So what happens when I have I can have a big pressure swing? What happens to the density? Liquids are hard to compress. There's not much change in density. So it's that change in density that causes your your linearization to break down. If the change in density is too big, our linear equation for the thermodynamics, we got from the adiabatic equation of state, will break down. So it's not really a problem here. Sound waves in water, you can have pressure swings that are comparable, are nearly equal to the equilibrium pressure. But what happens when you go beyond that? And everybody in the Navy should know this. Cavitation, right? So if I've got this pressure swing, I think this will this come up later? Yeah, this will, I can't remember. Let me do this quick diagram for you. Here's an acoustic wave has a pressure variation here, right? About some amplitude. And here's its amplitude. Oh, I'm sorry. This is not right. I want to look at the total pressure. So here's our total pressure, right? And here's our equilibrium pressure. Sound wave looks like this, okay, as a function of time. As you increase the amplitude, right, you get bigger and bigger amplitudes. Eventually, when you go down here, this is negative pressure. You can rip the liquid apart. That's called cavitation. It happens right around this region. Okay, I think we'll talk a little bit about cavitation later. That's a highly nonlinear, that's outside of linear acoustics. Okay. All right, so what about the particle velocity? Does it satisfy the wave equation? And in the process, we're going to get mathematical relationships with the particle velocity. Well, here's the, to look at that, let's look at the linearized Euler's equation. Here it is. And you'll notice something here. If we take the curl of each side of the equation, what's the curl of any gradient? 0, right? So we get an equation just in the curl of the velocity here. So I want to mention something here that I'm going to edit into the notes. KFCS are sloppy at this point. They don't do a proper job of what we're about to, of various things that we're about to do here. If you want to see it done properly, look in this book. I'll be writing this into the notes. Okay. What I'm going to present to you is similar to what's in that book. This is an excellent book. It's many people, including me, feel it's one of the best technical books ever written. Okay, I've referred to this book in my published articles much more than any other publication. And sure enough, there's a lot of acoustics in here. Okay, not only does it have a lot of fluid mechanics, but it has a lot of. They think of Landau and Lifshitz. They thought of acoustics as a special case of fluid mechanics. Okay, which I told you it is, right? So if you're serious about theoretical acoustics, you want to look at this book, and you may want to get a copy. Okay, it's very useful. All right, so KFCS say. Well, I didn't look carefully at KFCS, but they just do it sloppily. We're going to do it better. Here's what we conclude then. When we take the curl, okay, the curl and the time derivative are independent operations, so we can commute, right? We can bring the curl inside the time derivative here. Curl of any gradient 0, so I get this. Now you may remember that, so the time derivative of this vector function is equal to 0. Right? So that means, to be general here, that means that this could be some function of r. Because when I take the curl of this, when I take the time derivative of this, the time derivative, that's going to be 0. So that's all the information we have here. So we really can't conclude immediately. From this, we can't conclude necessarily that the curl of u is equal to 0. It could be a function of space, right? However, the time average of all linear acoustic variables is 0. They're always going to be oscillating equally, you see it right here, equally probable of being positive or negative swings. So if we take the time average here, and we can interchange operations, we're going to get 0 here. The time average of this is just itself. And if that's going to be 0, which it has to be, we can conclude that f has to be 0 here. So this is a proper way. I don't think KFCS does this. We conclude that the curl of u has to be 0. The next step is that we just have to do, that some of you may appreciate, is when you have a vector function that has no curl, it possesses a potential. Okay? Any function that has vector function that has no curl can be written as the gradient of a scalar. The standard place where this occurs is in electrostatics. So some of you may remember that for the electric field. The electrostatic field has no curl, so it can be written as the gradient of a potential, and that's called the electric potential. So the electric field is minus the gradient of the electric potential. Now, the minus sign here is for energy. There's an energy conservation. There's an energy connection with this potential right here. And I guess, you know what, usually people let's write it like that. Okay, so there's a connection of this with energy. There's no such connection here, so we don't use the minus sign here in this definition. So this is called the velocity potential, and we will, in this course, I don't think we're going to make a lot of use of it, but you make a lot of use of it in electrostatics, and the reason is, once the situation gets a little bit complicated, it's a lot harder to solve for, in general, it's harder to solve for the electric field than the electric potential, because this is a vector and this is a scalar. So this is one of the reasons that people run to scalar fields. When a problem gets complicated, they don't want to deal with a vector. Now in acoustics, we already have a scalar. We have the pressure, the scalar is the pressure. So we'll tend to solve problems looking at the pressure. So we don't have to run to the velocity potential. But there are cases where we will be using this, okay? And it comes because we have no curl, because this is 0. Now, this just naturally comes up here. What can we now have we've introduced another acoustic variable, the velocity potential. So it's natural to see what relations it satisfies. And if we look at Euler's equation, linearized Euler's equation, replace the particle velocity with the gradient of the velocity potential, we get this. And look what you can do here. You can take this over to this side of the equation and factor out the gradient operator and get this. So if the gradient on a function is equal to 0, that means this function is not necessarily 0, but it could be a function of time. So now to do this correctly, like it's done in Landau-Lifshitz, I believe, Landau-Lifshitz is almost always right. They almost always do things correctly, okay? I don't know if they did this, but if they didn't, they did something very similar, okay, related with other issues that we're addressing here. The gradient on a scalar function here, that scalar function, it can't depend upon space, because you have to have a 0 gradient, but it can depend upon time, right? Because the gradient of this is equal to 0. So we have some arbitrary function of time here. Okay, well that's not good. Can we get rid of it? And the answer is yes here. Because what's important about the velocity, well, the only thing that's relevant about the velocity potential is that its gradient gives us the particle velocity. So we call this capital phi. That's all that's relevant about this. I can add a function of time here and not change that. So the velocity potential is undefined to a function of time. So so you can do this trick here. You can bring this over here and absorb it in the phi. If you redefine the velocity potential by adding this function here, you'll see that when you substitute this in here, you kill this. So because we can always redefine the velocity potential to get rid of this function, we can essentially set this equal to 0. All right? So in the end, we get this, and we will use this relationship. For linear acoustics, this is a relationship between the pressure and the velocity, particle velocity potential. Okay, so now getting back on track here about the wave equation. The next step would be to ask, does phi satisfy the wave equation? Right? We know that p satisfies the wave equation. Does phi satisfy the wave equation? Well, the answer is yes, because the wave equation involves this operation, right, which is called the D'Alembert, sometimes denoted by a square like this. This is Laplacian, incidentally, as I think all of you know. A time derivative, it's easy to see that this time derivative operation commutes with the Laplacian. So from this, you can conclude that phi will have to satisfy the wave equation. And if phi satisfies the wave equation, you can show that the particle velocity u will satisfy the wave equation. You've got to do a little bit of it's not immediate here, but I don't want to get bogged down in this. We're going to show it from a different perspective tomorrow in a homework problem, that u satisfies the wave equation. The particle velocity satisfies the wave equation. Okay? Now I want to point something out to you here. I made a mistake in the past. Do you see that this is a bold R? Okay. In almost all textbooks, you can denote a vector like this. Often in printed books, they use a very bold, like this. And that's what I did there when I edited this in the past. That's a mistake. I'm going to change that. The reason is in KFCS, we reserve this for a complex, bold to denote complex. The use of complex numbers is so important. It makes life so much easier in all kinds of wave systems. That KFCS decided that the bold face is going to denote a complex quantity. Okay, so I'll fix this. Okay, so in the end, we conclude, and I'll add this, everything satisfies, all the acoustic variables satisfy the wave equation. Okay, that's what we've shown here, or come close to showing. And like I said, tomorrow we'll prove in a homework problem, we'll prove by a different route that the particle velocity satisfies the wave equation. Okay, so the next topic here is to focus on this quantity we call C, right? In acoustics, this is the speed of sound. Now, for a lot of other people out there in electromagnetic waves, this is the speed of light, right? You don't want to confuse the two. There's a huge difference, all right? They can enter into the theory very similar. You know, the speed of light is the speed of electromagnetic waves, but their values are hugely different. And also, the speed of light brings up the issue of relativity. If you're moving at any speed that's anywhere comparable to the speed of light, classical physics breaks down. Right? Newtonian physics breaks down, and you've got to use special relativity. So here's what we found, that when we derive the wave equation, the speed of sound is the square root of the adiabatic bulk modulus divided by the equilibrium density. If you substitute our expression for the bulk modulus, remember the bulk modulus is how the pressure changes with density, evaluated in equilibrium and evaluated, it's how let's see, it's still, hold on. If we, right. Okay, so it must be this. I want to be dimensionless here. Now, how do I know it's this? I was worried. I was worried about which way. How do I know which way to do this for the bulk modulus? Remember, liquids are very stiff, right? If you have a change in pressure, what kind of change in density do you have? Small. So it's a big number. The bulk modulus of liquids is much bigger. And what we're going to see eventually in here is that, you know, water has like roughly, I think it's roughly 1,000 times as dense as air, right? The bulk modulus is 1,000,000 times bigger. So that's going to have consequences, and we'll start to see them in a few minutes. Okay, so anyway, this should be right, and it's the fractional, so that's right. So we substitute that in here, and we get this. So this is our basic formula for the speed of sound, of linear sound, in any fluid. In any fluid. Most people write it like this, rather than deal with the square root here, we square it. And you have to take that derivative for an adiabatic process, because that's the compressions and expansions in linear acoustics are adiabatic. So this has to be done, we say, along an adiabat. Now I want to point something out here that will be useful for us a little bit today and a little more in the next chapter. Is this is playing the role of inertia, okay? And not surprisingly, if you increase the inertia of the medium, you slow down the waves. It's very reasonable, right? This is the stiffness. The bulk modulus plays the roles of the stiffness. When you imagine pressure, exerting a pressure, the density will go up if you pressurize it. And the higher the pressure goes up for a given density change, the bigger the bulk modulus. So this is playing the role of a stiffness here. And not surprisingly, the speed of sound, if you increase the stiffness, the waves move faster. Not surprising, right? So we can write down this kind of silly-looking nebulous thing here that I first saw, believe it or not, in an introductory physics, algebra-based introductory physics textbook when I was a teaching assistant. I never forgot it. This looks silly, right? But it really helps us in qualitative. It's not definite. This is not precise, right? But all mechanical waves will have this form. The speed of all mechanical waves will be the square root of something that's playing the role of a stiffness and something that's playing the role of inertia. So this is very general. As an example, waves on a string, right? You know from last quarter that the stiffness here is the tension, and what plays the role of the inertia is the mass per unit length. The units have to work out here, right? So these are going to have, for different mechanical systems, there's going to be different units here, but they've got to end up being length per unit time. So tension is a force. Bulk modulus has the units of pressure. They have different dimensions. But it's all saved by the fact that what plays the role of the inertia down here is the mass per unit length, not the mass per unit volume. Now there's one more boxed relationship that'll help us for just qualitative reasoning. And that involves the impedance. You know from last quarter that the wave impedance for waves on a string is the mass per unit length times the speed of waves. That should ring a bell, right? The wave impedance. We're going to find in acoustic, the same thing happens in acoustic waves. It's just rho naught c. All right? And we'll prove that later. But what I want to point out right now is when we take this and multiply by inertia, we end up with this, okay? Now again, this is not definite, this is not precise, but this is going to bias a lot, all right? And if I remember, I will, when we hit this in the next chapter, I will, when we do reflection and transmission, I'll point out why that introductory algebra-based physics, you know, it's algebra-based as opposed to calculus-based, right? Do you guys, okay. Why I think this was a long time ago, but why the book, why they did this? I think they were after something that we're gonna derive in the next chapter, and I'll show you a demonstration of it. Okay. So the speed of sound obviously depends upon the equilibrium state. If you change the inertia, the stiffness, you're going to change the speed of sound. And it will vary from one fluid to the next, too. The natural thing to do next is to look at air. Because for air, we know what an adiabat is. We know the pressure-density relationship for adiabatic changes. You may remember it's given by this. So all we have to do is this is equivalent to this PV to the gamma is equal to a constant. All we do is shove it into here, into our speed of sound. Okay, it's how the pressure changes with density adiabatically, and you evaluate it in equilibrium. So you go through here, I won't go through this, but you can look at it if you're interested, and we'll do similar things in homework. You go through and carefully do this derivative, and you end up with this expression right here, which can be put in a much better form, okay? We use the equation of state. This is the equilibrium state, the pressure divided by the density. We can use the equation of state to simplify this, and we get this formula for the speed of sound in an ideal gas. So this is a well-known formula. We'll use it a lot. And remember, gamma is the ratio of specific heats. This is the universal gas constant. This is the molar mass. That's the absolute temperature. And something very remarkable has happened here. You probably don't see it. But what if I have a gas here, okay, and it's connected thermally so there's a constant temperature. And let's say I press in the piston. So I've changed the medium, right? How does the speed of sound change? You might think, oh, it's stiffer now, right? So you're going to increase the speed of sound, but it's also more dense, right? In fact, those two things scale by the same amount. When I push this piston in halfway, I think I'm getting dangerously close to a quiz question here. So I better back off. When you increase the density, you also you increase the inertia by some fraction. You increase the bulk modulus, or the stiffness, by the same fraction. And that's what this formula is telling us. The speed of sound in ideal gas depends only upon the temperature. So because I'm keeping the temperature constant here, the speed of sound can't change in there. And that escapes a number of people, even sometimes acousticians, believe it or not. So this is a nice simplification here. And it's happening, the reason it's happening is, from a qualitative point of view, is from this right here. They both increase together. So as long as you keep the temperature the same, the speed of sound will be the same. Now, I need to warn you, this is only true for a gas, in general, for a gas. What happens for water? Okay, suppose I had water in here, and it just doesn't really matter, but you can keep that there. Suppose I press on this. Okay, what happens to the stiffness? It's stiffer. The sound wave is going to travel faster. What happens to the inertia? Hardly anything, right? Unless you're at the bottom of the Mariana Trench, or I don't know, unless you're in an extreme situation. So, for sound and water, for sound and water, it's not just dependent upon the temperature, it depends upon the pressure. Okay, so as you go deeper in the ocean, as long as you don't go very deep, the density doesn't change much, but the pressure goes up, the speed of sound will go up, if the temperature stays the same. You know, it depends upon both temperature and pressure. Equilibrium temperature and equilibrium pressure, it depends upon both of those. Whereas an ideal gas only depends upon the temperature. So we'll do examples of this in the homework. There's one more just real quick thing. Here's the way that people often, we don't like to deal, this can be messy, the molar mass, you know? So when you need to get values quickly and you're changing the temperature, something like that, we take a ratio of this with the speed of sound at some reference temperature. It's usually taken to be 0 degrees Celsius. So if you take a ratio, you can easily see that the speed of sound, in terms of the speed of sound at 0 Celsius, which is 273 Kelvin, is going to be given like this. Basically, this is just a statement that the speed of sound depends upon the square root of the temperature. Okay, there's a proportionality constant here, and this is the proportionality constant that we get from our reference temperature here. Here's the speed of sound this is in air. Okay, this is all in air. Speed of sound in gas. So for the important case of air, this is in general for an ideal gas. For air, this is the speed of sound at 0 Celsius. And I don't remember this. For this class, you may not be able to not memorize. I think you're naturally going to memorize this. 343 meters per second. We're going to use it so much. That's the speed of sound in air at room temperature, which is 20 degrees Celsius. Okay, any quick questions? Sorry, I went over a few minutes. Any quick questions? Okay, so try to look at those problems, right? Come in a little prepared or more prepared. And we'll spend the whole time tomorrow discussing problem set 1. The problem sets are posted in Sakai.
And then the quiz will be tomorrow?
Yep, I'm gonna post it tomorrow, probably in the morning or the afternoon. It'll be on Sakai. And you'll have a week, roughly a week. You'll always have a weekend. Always that.
Next Friday.
Well, that's the
Problem set.
That's the problem set. Okay. The quizzes, I'm going to ask for them on Thursday, so I'm going to have a lot of grading to do, and you can't do it all at once. So I'd like to be able to start Thursday evening. So I'm going to have them. They'll be due 1 week they'll be due on Thursday, probably towards the afternoon, 4 p.m. Pacific time.